Hello everybody, Namaskar. Initially I have already discussed that why the isenthalpic expansion in a refrigeration system has been undertaken instead of the isentropic expansion, so that the turbine can be used to get the isentropic expansion, but that is not used. Instead of that, the isenthalpic expansion, that means the expansion devices is used for the expansion process in the vapor compression cycle due to the cost issues. And I have already studied the different modification of the vapor compression cycle. So in this class I will discuss the system with expansion turbine. Okay, so in this modification, basically the expansion turbine is used instead of the expansion devices in a refrigeration system. So in this cycle or system, basically the process 3 to 4 has been modified by using the expansion turbine instead of the expansion devices, and other processes are same as the basic vapor compression cycle. So the 1 to 2 process is the compression process, 2 to 3 process, this is basically the isobaric heat rejection process, and 3 to 4 this has been changed. This is now the expansion process in expansion turbine, which turbine will produce some work, and that work can be used in a compressor. So the net work needed for the compressor that can be reduce, so which will ultimately give the overall performance improvement of the system. And after the expansion process at point 4, the quality of the vapor that can be reduced, because this is close to the isentropic expansion process. So the evaporation capacity or the cooling capacity that can be improved. Okay, so 4 to 1 is again the same as the isobaric heat addition process. So if I represent this in a TS or PS diagram, so this is our basic processes of this cycle, and this process we can now plot it in the temperature entropy and pressure entropy diagrams. So in a temperature entropy diagram, now the process in a expansion turbine, this is the process 3 to 4. So 3 to 4 is, this is the isentropic process, and 3 to 4 this is the actual process. By considering the irreversibility in the expansion process, so that expansion process is not actually the isentropic process, that is deviated from the isentropic process, or that is the non-isentropic process or irreversible process or actual process. This is 3 to 4, and in this diagram you can see that for the basic cycle we have assumed that the process 3 to 4H, this is the isenthalpic process. So same thing we can represent in a pH diagram. So this you can see that the basic difference, the 3 to 4, this is the isentropic expansion in a turbine, and 3 to 4 this is basically the actual expansion in a turbine or adiabatic expansion in a turbine. So by default this process is assumed as a adiabatic process, and whereas the 3 to 4A, this is the isenthalpic expansion in a expansion devices, which is for the basic refrigeration cycle. So same thing we can represent in a pressure enthalpy diagram also. So 3 to 4A, this is the isenthalpy process. So 3 to 4, this is the process in a turbine. So we can easily see from this diagram that the enthalpy at point 4, this is less as compared to the enthalpy at point 4H, or we can say that the quality at point 4, this is reduces as compared to the quality at point 4H. So that means by using the expansion turbine, the quality of refrigerant at the inlet of the evaporator that will reduce, and which will ultimately give the higher enthalpy difference in a evaporation process or heat addition process, which will ultimately rise in the cooling capacity of the system. So for the calculation for this system, actually the other processes like the process 1 to 2, that is the compression process, and by using the refrigeration table or the saturation table of the refrigerant, that point 1 and 3 both are basically the saturation points. So point 1 is the saturated vapor and point 3 is the saturated liquid. So and the process 1 to 2, that is the same as the process we have discussed for the basic cycle. So that's why the calculation procedure to calculate the enthalpies or entropy at the point 1, point 2 and point 3, those are basically the same as the basic vapor compression cycle. So that's why in this time I will not discuss how to evaluate the enthalpies at 1, 2 and 3, which has been already discussed. So that's why I will only discuss that how we can get the enthalpies or entropy at point 4s. So we can use this to calculate the point 4 at enthalpy at point 4. Initially we can use the isentropic process, that is the 3 to 4s. So the entropy at point 3, that is equal to entropy at point 4s, and this is the basic equation to calculate the entropy for the liquid vapor mixture. So x4s, this is the dryness fraction at point 4s. So by using the first equation we can calculate what is the quality at point 4s, and then by using the second equation we can calculate what is the enthalpy at point 4s, and after that we can use the isentropic efficiency of the turbine, that is basically H3 minus H4 by the H3 minus H4s. So basically isentropic efficiency, that will say that how the process is deviated from the isentropic process. So the isentropic efficiency of the turbine that can be defined as the actual work by the isentropic work. So this is basically just opposite of the definition of isentropic efficiency for the compressor. For the compressor, basically the ideal work that is less as compared to the actual work. So that's why the isentropic efficiency of the compressor, that is defined as a ideal work by the actual work. But in case of turbine, the actual work that is less as compared to the ideal work. So we can assume that the actual work we are getting less due to the loss of work due to the irreversibility of the process. So that's why the actual work that is less as compared to the ideal work or isentropic work. So from this definition we can easily see that if we assume the isentropic efficiency of the turbine is 100%, so the process 3-4 will become a isentropic process. So that means the process 3-4 and process 3-4s both will be same. And if we assume the isentropic efficiency of the turbine is 0, then we can see that that process will become a isenthalpic process. That means the H3 is equal to H4. So that process is equal to the process 3 to 4H. Okay, so the isentropic efficiency of the compressor, the expander, that can be used to calculate what is the actual enthalpy after the expansion, that means the H4. So if the isentropic efficiency of the expander or turbine is given, then we can calculate the enthalpy at point 4. And if you want to again calculate what is the entropy at point 4, then we can calculate first the dryness fraction at point 4, similar to the second equation, and similar to the first equation, then we can calculate what is the entropy at point 4. So then ultimately we can calculate the cooling capacity, compressor work and turbine work. So cooling capacity is this is depending on the H1 minus H4. So the H1 minus H4, that is obviously more than the H1 minus H3. So from here we can easily conclude that the cooling capacity by using the expansion turbine, that will improve. Then the compressor work H2 minus H1, that will be same as the basic cycle, but additionally we are getting the turbine work, that is basically the H3 minus H4. So H3 minus H4, this is the turbine work we can get, and if you couple the compressor and turbine, then we can see that the net work needed for the system, that means the compressor work minus turbine work, that can be reduced. So, for this system, from the basic thermodynamics, we can easily explain that the compressor work that is always higher as compared to the turbine work, because you know that for the same pressure difference, the work is basically depending on the density or the specific volume of the fluid. So, higher specific volume of the fluid will give the higher work for the given pressure difference, and lower specific volume will give the lower value of the work for the given pressure difference. So, for the same pressure difference in case of compressor and turbine, because in case of turbine, that is basically the initially liquid phase, and then after that is the two phase. So, obviously for this case the density is high as compared to the density which is handled by the compressor. So, the turbine work is very less as compared to the compressor work. So, the net work that will be negative, that means the net work that we have to given to the system, and that is basically the compressor work minus turbine work. Okay, so due to the some work produced by the turbine, the net work input to the system that will reduce. Okay, so ultimately if I define the COP of the system by the ratio of the cooling capacity by the net work needed for this system. So, the cooling capacity by using the expansion turbine that will increase, and the net work needed for this system that will reduce, because we are getting some work in the compressor. So, please make one correction that the W dot C, second term W dot T, turbine work. So, that compressor WC minus WT, that will give the net work input needed for the system. So, this ratio, that with the COP, that will be improved, that means the numerator will increase and denominator will decrease. So, the COP of the system that will increase significantly by using the expansion turbine. So, this conclusion ultimately we can make that the cooling capacity increases, net work input that is decreases. So, the COP of the system that increases. So, now this increase of the capacity, cooling capacity, so that is basically obviously depending on the type of refrigerant used. So, to prove this statement, I can give on simulation data for the three refrigerant R32, R290 and R717. So, in this graph, the increase of cooling capacity that has been plotted against the turbine isentropic efficiency. So, I have already told that the turbine isentropic efficiency that is equal to 0. So, that is basically represent the isenthalpic process basically, and if the isentropic efficiency is on or 100%, that means the process is the isentropic process. Okay, so actual isentropic efficiency that is obviously in between that, and depending on the turbine used, that efficiency can vary. So, this graph is basically say that how your cooling capacity is varying with respect to the turbine efficiency. So, obviously the initially that is 0, because this is the isenthalpic process. So, there is no work produced by the turbine. So, for this case the improve of the cooling capacity that is basically equal to 0 initially. So, but for the different refrigerant, the variation with respect to the isentropic efficiency that can be defined for the different refrigerant. So, the considering these three refrigerant, we can easily see that the R290, that means the propane, this can give the highest amount of cooling capacity increase by using the expansion turbine, and this data is basically plotted for the evaporator temperature of minus 20 degrees centigrade and condenser temperature of 40 degrees centigrade, and the isentropic efficiency of the compressor that is 80%. Okay, so based on this data, we can say that by using the ammonia, we can get about 3% improvement of cooling capacity. By using the R32, we can get about 6% improvement of the cooling capacity maximum, and by using the R290, we can get about the 80% improvement of the cooling capacity. Now we can see that how much net work output can be decreased by using the expansion turbine. Okay, so the decrease of net work can be defined by this equation. So this is represent the percentage decrease of the net work input to the system. So for this case, for the same data and with the same refrigerant, we can see that what is the percentage of saving of compressor work by using the expansion turbine. So for this case also, we can see that the percentage saving is minimum in case of ammonia. So this is up to 8% decrease we can get in case of ammonia. In case of the refrigerant R32, this amount is approximately 14 to 15% maximum. So 14 to 15% work compressor work saving we can get by using this refrigerant, by using the expansion turbine, and about maximum of 18% or 19% decrease or saving of compressor work we can get for the refrigerant propane by using the expansion turbine. Now, now we can see that what will be the improvement of COP by using the expansion turbine. So we can get the increase of COP by using this equation. The COP of the system with expansion turbine minus the COP of the basic cycle, that means with the expansion devices, by the COP of the basic cycle. So for this case, the numerator will increase and denominator will decrease. So obviously the increase of COP by using the expansion turbine, that is significant. So in case of ammonia, we can see that the maximum improvement is about 10 to 11% by using the expansion turbine. In case of that R32, we can get about 25% or 26% maximum improvement by using the expansion turbine, and in case of propane we can get about more than 30% improvement of the COP by using the expansion turbine. Okay, so from this graph is basically says that for all the refrigerant, if we use the expansion turbine, we will obviously get the improvement of COP, significant improvement of COP, and that improvement of COP can be vary or that is depending on the refrigerant use. Okay, so the improvement of COP is basically represent the decrease of running cost of the system. That means for the given cooling capacity, the compressor work requirement that will be less in case of the higher COP of this system. Okay, so finally we can summarize the advantage and disadvantage by using the expansion turbine. So that increase of refrigeration capacity, which we have already seen that by using the expansion turbine, the refrigeration capacity or cooling capacity that will increase, and decrease of net work input, that also we have seen from the numerical values that the net work input required that will be decreased by using the expansion turbine. So this will ultimately leads to the improvement of the COP of the system. So what I have already told that the COP increase means the decrease of running cost. That means for the same cooling capacity, what is the compressor work required, that will be less in case of higher COP. So if the COP will increase, so by using the expansion turbine, COP increases, so the running cost of the system for given cooling capacity that will decrease. but there are some disadvantages. So first disadvantage is the initial cost of the system that will increase. So here basically we are using the extra component turbine, and turbine cost is very significant or very high if we compare with the expansion devices for the basic refrigeration system. Expansion devices cost, that may be the expansion valve or the capillary tube, both cost is very negligible as compared to the cost of the turbine. So that means the initial cost of the system that will increase significantly. And second is that when we are using the turbine, so turbine size is also very high as compared to the size of the expansion devices, that may be the capillary tube or the expansion valve. So that means the space requirement by using the expansion turbine, that will also increase. So this is the main reason that expansion turbine is generally not used in the vapor compression refrigeration system. So that means that by using the expansion turbine, the initial cost will increase, but the running cost will decrease. So the which will be more significant. Okay, so most of the cases the initial cost increase, that is much more significant as compared to the electricity saving or saving on running cost by using the expansion turbine. So that's why the expansion turbine is generally not avoided in a vapor compression refrigeration system. Okay, so some that attempt recently has made that how we can combine the expansion turbine and compressor, so that we can get the both expansion and compression in a single devices. So for this case the cost of the system will also reduce, and also the space requirement, okay, so that will be also reduced, because we are using the single component which will give the dual operation, that means the compression as well as expansion. But that attempt has not been successful. Okay, so that's why the present scenario is that the turbine is not used in a vapor compression refrigeration system. Okay, thank you.